So far today we've heard lots about CubeSats. Basically what's going up in space. I'm going to talk about what goes on 30 metres up from here. So our ground station is an amateur radio station. It's an amateur club station. It was originally developed by BlueSat up until the delivery of ECO, and then after that AXA joined in and helped BlueSat develop it from then on. About a year ago, or 10 months ago, the ground station actually went fully autonomous, so we can have a real life and get on with our regular day. And during that time, the ground station's evolved both in software, mostly in software and hardware. I'm going to talk a little bit about software evolution and have a look at the stats on how the ground station has operated since going fully autonomous. June put up a picture of our first beacon, so to speak, basically when we first established comms, and it was a screenshot. And on that screen you saw gpredict running and CSP term. And these software, or gpredict and handle, basically provides you with the ability to track the satellite's position with an antenna and the Doppler of the radio. And CSP term is basically our ground node to talk to and communicate with the satellite. This required a person to sit there at all hours of the day, maybe with remote access if you had TeamViewer set up. But regardless, you had to sit there and man the 4 AM pass, and that's literally what we were doing. The software was also a little bit clunky, it was rigid, it was buggy, it would crash a lot. We couldn't really change it. We basically had no control over it. So then, moving forward, the first thing we did was we implemented the app system, I called it, which is basically just a hack of all these different Unix commands so that we could tee up the batch file and run off all of our commands at night, get a good night's sleep, and come back and have a look at what happened in the morning. In parallel to that, after we got that cron and at system running, I started developing a Python module to replace the gpredict chain, and that basically was going to circumnavigate essentially the single-threaded nature of gpredict. If you had a radio that was slow to respond, the rotator would stop. So this was just not going to be acceptable moving forward. So after that Python module was implemented, it was technically superior, it was running fine. It wasn't user-friendly. You basically had to SSH in and jump around the terminal to figure out whether or not you could ping the satellite or whether or not you got that beacon data 3 hours ago. But it technically outperformed the previous solution, so we knew that this is what we wanted to do moving forward. So Will and I, one of the other students, put in the hard yards and developed a full system. Basically now we have a web interface, so we can either control it from home or you can go up to the shack. But essentially now it's a lights out system. We go into the shack maybe once a month to check on the systems, see how dusty it is. That's about it now. Other additional features was the automated scheduling and command. So now, instead of manually writing a batch file to say, give me this file, give me that file, or turn this on or off, you can basically write out a wish list, and then the software will go through that list and determine whether or not it needs to retry a command, or whether that file was corrupted, or it needs to do this command in order to achieve what you wanted. So we're moving slowly higher and higher and higher, and eventually I just want a big green button that says do mission. but that won't come. A little bit more of a complicated, look at the software architecture. So now instead of just a human sitting there physically editing these files, so these blue files are the files edited by humans, they can edit it through any one of these remote interfaces here, or they can physically go into the machine and change it. I won't go too much into this unless if anyone has any questions on the software architecture, but essentially now what we have is a web server, an SMTP client, so if you want, you can get email notifications if you did get that beacon data down, and an FTP server, so we can just log on and download all the files that we want. And a look at the actual system architecture. And probably one of the biggest problems we had was budget, resulted in this, was the use of amateur radio components. At the time of purchasing the gear from GomSpace, that was nearly even the prescribed solution. was to have a TNC and manage a radio base station. So this radio chain was kind of prescribed to us, but then the rotator was just what we could get. And overcoming the difficulties with that hardware alone was probably 60% of the challenge. Look at the architecture here. We can see this is the PC that actually runs the system. So this is the thing scheduling the passes, sending the commands, and the thing that you log into. In the same room, there's a mission server. So at the end of a pass, it'll upload all of, basically save the state of the satellite. So this is your 70% of the file. This is the last command that was executed. And what can happen, which has been rolled out, but hardware limitations meant that it hasn't really gotten anywhere, is that you can roll this out anywhere in the world. So say over in France, they roll out this same software. After a pass in Sydney, it pushes the state of the satellite to the mission server. France will then pull that down 2 minutes before their pass and pick up literally the byte after where you left off in Sydney on that download. Okay. Looking a little bit at some of the stats on the logs to date, since we went fully autonomous in August last year. So this is the stats on where the antenna has pointed since August last year. And there's not too much of a surprise in the fact that the satellite spends most of its time at low elevations. Sorry, I should say this is a linear colour scale and this is a log colour scale. The southern sky is busiest, also expected. We're in the southern hemisphere and the inclination of eco is larger than our latitude. Interestingly enough, this little hole in the sky had me confused for a little while. This is actually a combination of our latitude, its inclination, and the 5-degree elevation mask that we apply. So we actually don't get any passes down at that little bit. Unfortunately, that's a very clear part of the sky. Looking at the azimuth histograms in polar and Cartesian form, we can see that obviously the southern sky is busiest here and here. For the northern sky, there's that hole I was talking about. There's two nice little peaks here at say 36 degrees and 180 degrees. Anyone want to guess what that is? It's not a bug. That's where our engineering model lives. So from our ground station, we can actually point the ground station to an antenna on the roof, which runs down into our lab, and we can talk to our engineering model with the same software that talks to the real thing. And similar in elevation, we've got our 0 degrees, so that's peaking because the ground station will point to AOS and LOS and wait for 2 minutes at the start of the pass, and obviously the satellite's slowest at that point as well. And then again, the elevation of the EM was 4 degrees because we had to avoid multi-path locally. The evolution of the link. So in CSP term, there's a command called com-RSSI. Basically polls the radio on eco for the RSSI, the received signal strength, and the RF error, the error in the carrier frequency going up. As part of all of our passes, we schedule in some com-RSSI commands just so we can keep a tab on how the link is changing over time. And it's also useful because we can use that to then close the loop, maybe adjust the radio or basically monitor the health of the thing as well. If you look at how many com-RSSI results we've observed in the 10 months since going on fully autonomous, the edge is obviously just incomplete months. I'll let you guess where the 2 relocations of the ground station occur. And if we look at the RSSI over time, basically what we can see is on a monthly average basis, if we fit that, the RSSI is basically constant, nearly for the whole last year. So we're confident that the link hasn't degraded in both the space and the ground segment. But interestingly enough, if we look at the RF error, we can see that slowly it's drifted from plus 500 to minus 500. And this really isn't a problem because this is the RF error on the uplink, and Nanocom's the radio on eco itself. It's quite tolerant, it can handle a couple of kilohertz error. But what we do need to do is we need to confirm whether this drift is introduced on the radio, on the satellite, or on the radio in the shack. That's something we need to figure out moving forward. And I'll leave it at that, 10 minutes. And any questions for our little mascot here?
That's very good. So time for questions, maybe 1 or 2 questions. Yep.
Is your software stack available for other people to download and use?
It could be if I cleaned up the comments. Yeah.
I take that as a yes.
I'm quite rude to myself in the comments sometimes.
Good for you for writing comments.